SpaceX has just revealed the nakedness of the Super Heavy booster, which will have several propellant pipes connected to 33 Raptor engines. The pipes look so messy like spaghetti, and to the eyes, it doesn't make sense. More like scattered tiny pipes that no one can spot the functions except an experienced rocket engineer. Stick around as we reveal the 33 Super Heavy booster engines that SpaceX has finally shown for our viewing pleasure. SpaceX fans are still staring at the Super Heavy and imagining how this amazing stainless steel monster is created. Without the Super Heavy rocket, SpaceX's Starship will be unable to reach Earth's orbit. The first challenge to overcome is getting off the ground. A fully fueled Starship weighs around 1,400 tons. One Raptor engine produces approximately 200 tons of thrust, so 33 Raptor engines will produce 7,000 tons of thrust, which is 5 more than the overall weight of the Starship, so the Starship can lift off and break the Earth's atmosphere with this thrust. According to current plans, there will be roughly 3 sea-level Raptor engines and 3 vacuum-optimized Raptor engines. With full fuel tanks, the Starship would require 7 sea-level capable Raptor engines merely to hover, and it would use a tremendous amount of fuel merely to hover. To accelerate upwards, reasonable fuel consumption and safety, at least 9 sea-level engines would be required. With only 8 engines, the thrust-to-weight ratio would be about 1.14, which would mean that at the moment of liftoff, 87.5% of the thrust would be used to fight gravity and hover. Only 12.5% would be used to lift and accelerate the craft upwards. The next problem is to determine the orbital velocity. Assume we only had those 9 sea-level Raptors and that we replaced our 3 vacuum Raptors with 6 of those sea-level Raptors. The particular impulse of a sea-level Raptor is around 350 seconds. The vessel weighs around 125 tons. We can compute that burning 1275 tons of fuel results in a delta V of 8.3 kilometers per second for a 125-ton vehicle. Low Earth orbit travels at a speed of 7.8 kilometers per second, which is less than 8.3 kilometers per second, but because a large portion of the thrust is utilized to combat gravity early in the flight, the actual impulse for climb and acceleration is substantially lower. To enter Earth orbit, a delta V of around 9 kilometers per second is required. This is faster than the 8.3 kilometers per second of Starship's sea-level Raptor engines, and we'd need those 9 sea-level engines to lift off and fly the first several kilometers. Thus, how about having both sea-level and vacuum engines? So consider reintroducing the 3 vacuum engines and the 9 sea-level engines to improve particular impulse. Those engines add around 5 tons to the boat's weight, but they can now provide up to 50% of the acceleration instead of the sea-level engines, and our specific impulse is not 365 seconds. 1,270 tons of propellant results in a delta V of 8.5 kilometers per second for a 130-ton craft. Slightly better, but still insufficient. Getting to Earth orbit with no payload and no fuel, on the other hand, is completely pointless. The vehicle could be refueled in orbit, but the tankers would have to be able to transport that fuel as part of their payload. In addition, the tankers would require adequate fuel for deorbiting and landing. Landing necessitates the use of an additional 10 tons of fuel. So in practice, the craft's weight would need to be reduced to fewer than 100 tons to reach orbit and have adequate fuel for re-entry and landing. And if we wanted to fill the tanks of another Starship so that it could fly further out, such as to the moon, we would have to hoist 1,300 tons of gasoline. Keeping the vehicle's weight under 90 tons and having a useful cargo of 10 tons in reusable SSTO mode implies 130 flights for the tanker to fill the tanks to the one craft heading for the moon. Even after reducing the tanker weight to less than 80 tons, 65 tanker flights were required to fill the tanks. So practically no, as it is now planned, or with relatively minor modifications, Starship cannot reach Earth orbit without Super Heavy, even with 0 payloads. Even with massive weight-saving modifications, the performance without Super Heavy would be so poor that an insane number of tanker flights would be required for any reasonable mission to higher orbits or other destinations than low Earth orbit. And the aforementioned are are evaluations that has been considered to make the overall Starship triumph. Let's get down to some other crucial questions we might be curious about. Why are there so many engines on SpaceX Starship boosters? Wouldn't having one or a few huge engines be more fuel efficient? The first thing to note is that they are rockets. They blast flames like it's a fad. They are operating wide open on launch, and if one of the huge motors fails, both the rocket and the very expensive payload are lost. Multiple smaller rockets are less stressed and more dependable. Furthermore, some are redundant. If one fails, the other might be throttled up a little to compensate and still fly. The same is true for landings. With more motors than are required, and without the lower stages, which reduces a lot of weight, there is spare capacity to take up the load if a motor fails. Rocket engines are currently nearly as efficient as they can be. Whether they have 1 or 10 engines, they convert more than 95% of their chemical energy to thrust. The effectiveness of a rocket engine is mostly governed by the fuel used, which dictates the composition and velocity of the exhaust. Regardless of the engine size, the Starship is locked into a specific impulse of roughly 300 to 330 per second at sea level and 350 to 370 per second in a vacuum by consuming methane and oxygen. Specific impulse is a property that governs how much fuel is used for a given quantity of thrust. A particular impulse of 350 per second indicates that the engine consumes 1 pound of push per second to create 350 pounds of thrust. If it has 10 engines that provide 35,000 pounds of torque, it'll consume 1,000 pounds of fuel each second. If it has a single engine that produces 350,000 pounds of thrust, it will use 1,000 pounds of fuel each second. You've probably heard the expression, "That's not rocket science," and this is exactly what it is. Everything is a balancing act, with a sacrifice in one area resulting to the required work done. The Falcon rocket series was created from the ground up to perform something never done before, and that is re-entering the atmosphere engines first at supersonic speeds and then land propulsively. Bells on atmospheric rocket engines compromise the sea-level performance and near-vacuum performance. Observe a launch and watch how the exhaust spreads as the speed increases. That sideways spread represents lost propulsion. A larger bell could collect it, but the vehicle's footprint would have to be larger, so the bells don't collide. Remember that each of those engines must gimbal to adjust the flight. As a result, they require space to maneuver. The engines must have enough reserve power to ensure that the others can still achieve orbit if 1 or 2 fail. Compared to a Falcon 9 rocket, a single Super Heavy booster has approximately 8.5 times the fuel on board. However, it is just slightly less than 4 times the number of engines. On a Starship, everything is larger. You may be wondering what all the spaghetti behind the booster is meant to do. No rocket has ever been delivered to the launch site without the engine covers. This Super Heavy booster sans a skirt that isn't even blushing. We can practically stare at its private parts straight on. Engine connections and gimbal components. A closer inspection displays the whole engine configuration. A 20-engine outer ring without a gimbal mechanism and fixed in place. Those are the turbochargers. They exist merely to provide the necessary thrust into orbit. For almost 3 minutes, I was static, unable to steer, and simply blasting. Because they don't move, they don't require flexible connections. Therefore, they're static pipes with a very small flexible end. Then there are the internal engines, and things get a lot dirtier. There are 13 engines and more than 50 connections. Intake of methane and oxygen, inlet for spinning up, inlet for hot gas, backflow and autogenous pressurization connections to power sources, telemetry and sensors. It appears to be a jumble at first glance, but everything here makes logic and has a function. It's only that there are so many SpaceX Raptor 2 engines that the avionics must feed and regulate. From the first full cryogenic test on a Super Heavy booster in the Starship program's history through the following test. As mentioned in the last episode, the main objective of these 33 hydraulic ram beasts is to see if the structural integrity of the booster's hull can withstand the simulated thrust of 33 Raptor engines at full power. They put the hull through its paces as though it were in full flight. Do you believe the 33 engines will burn successfully and land the Starship on Mars? You can also check how this SpaceX Super Heavy booster is the biggest monster so far. Just click on the video.